I will dive into the detail of some of the acronyms that Javi just mentioned, SDII and IAC. But just a preface, you may remember that last semester, we have 8 projects that are funded through the Smart Transportation Infrastructure Initiative, 4 of which were featured last semester, and then the next 4 will be featured this semester. One of the projects will be right after this short overview of IAC and SDII. And with respect to IAC, it's the Illinois Autonomous and Connected Track. And today I'm happy to share some of the thoughts we have in planning this new test facility, which will be geared to understand what we need to prepare for the next generation smart mobility. I would be remiss to not acknowledge the main lead of this project and also the ICT director, Professor Emmanuel Kadi. So just as a background for the Smart Transportation Infrastructure Initiative, it started in 2018 with a grassroots meeting. And interestingly, what was found back then, apart from our small family in the Illinois Center for Transportation and ICT, was that over 160 faculty at the University of Illinois expressed interest in becoming part of this initiative. And particularly their expertise were closely related to transportation and to smart mobility. And we have identified 8 bins or 8 columns, if you may, where we have organized these expertise, which is under the umbrella of the SDII initiative. And currently, apart from planning the track, SDII is also focused on building our partnerships and collaboration through different paths, through public agencies, private industry, and also academic institutions and technical and community colleges. So that's kind of the general overview of SDII in planning IAC. Now, the importance to Illinois, I just want to zoom out of IAC for now, and wanted to focus, the motivation in even creating such facility. In the past 6 months, unfortunately, there has been an 18% increase in traffic-related injuries, over 20,000, as you can see, for the United States. Particularly within Illinois, it has been reported in the 2021 report that there's over 1,200 deaths related to motor vehicle crashes. And unfortunately, that cost is, related or equivalent to nearly $6 billion. And I guess this is a terrible metric to say, but each fatality is just estimated to cost nearly $2 million. And the top 5 reasons for such crashes are attributed to driving behaviors, driving too fast, not being able to keep in the proper lane, yielding right away, and distractions, whether that's through a cell phone and also alcohol and drugs. Here I've highlighted or put the first 4 in red to highlight that, this is something to think about, that as connected autonomous vehicles and trucks increase in our roadways, these are some things that can be mitigated or hopefully be fully addressed. So we mitigate and reduce these crashes, which are attributed to driving behavior. Now, with respect to our environmental condition, in the US, over 100,000 premature deaths are related to air pollution, and particularly related to particulate matter. And unfortunately, 53% of that is attributed to the realm of transportation. Some studies have identified that by introducing electrification, so the facility to support electric vehicles could actually save over 3,600 lives per year in relation to $72 billion in health effects, with that goal of increasing electrification by 2050 in the US. And correspondingly, the Oak Ridge National Lab also estimated in their study in 2017 that up to 44% of energy savings can be reached that's related to electric heavy-duty trucks. So quite a good amount of savings, not only with respect to air pollution, but also with the energy usage. And for Illinois, just last fall, we have some recent legislation that was passed in September, particularly the Climate and Equitable Jobs Act, which the main goal is to be carbon-free in the power sector by 2045 and 100% use of clean energy by 2050. The month after that, the state also passed the Reimagining Electric Vehicles in Illinois Act, or the REV Illinois Act, where the goal was to reach 1 million electric vehicles by 2030, and also identify what are the tax incentives that can be created both for EV manufacturers and also suppliers. So the whole scheme of where EV will be touching. And so at this point, some of the other studies that can also improve congestion, which we can also tie of how it can change Illinois. The studies have reported that, leveraging the connectivity between the vehicles, even in platooning, is simply how they're placed as they're moving through our highways, could improve fuel economy by 39%. And because of that connectivity, one may anticipate that we can increase speed, which also can be related to improved traffic flow, reduction in delays by 15%, and assuming a 90% market penetration of connected autonomous vehicles, it may double our roadway capacity, as you can see here, which will be really nice as it can reach our goal in optimizing traffic flow and reducing congestion simply by leveraging that vehicle to everything connectivity. Now, with respect to safety, that's also something that the introduction of CAV&T properly done can really improve, as that connectivity can also leverage to providing more reliable travel times. And as you can see here, researchers have estimated that as you increase market penetration, that the traffic conflict can range from 47 to 94% when the market penetration ranges from 25 to 100%, which what we can anticipate is it will help us minimize accidents and fatalities by leveraging how we can create new protocols and also extending that to public education. And correspondingly with climate change, with the changes that I've hinted at or pointed out previously, that some researchers have identified that by implementing eco-driving and platooning, greenhouse gas emission can be reduced by 35%, and correspondingly with the eco-traffic signaling, 19% reduction in greenhouse gases, and electrification can also further reduce the greenhouse gas emissions by 63%, which, connected to some of the laws that Illinois just passed or have adopted just last fall, will help us meet this goal of developing net zero emission goals and also an electrified mobility. And so this is what we're excited about, where IACT could come into play in trying to reach these goals with respect to congestion, safety, and climate change, and also workforce development is the development and construction of the Illinois Autonomous and Connected Track. Here, what we're taking a look is the Google map view of the IACT property limits as a baseline. This is undergoing conceptualization as we speak, so it may be changing. But what I wanted to highlight is we're looking at Rantoul, Illinois, which is 20 to 30 minutes drive north of the University of Illinois. Apart from the facility we're aiming to build, the proximity to other modes of transportation. We have an active airport here, which used to be part of the decommissioned Chanute Air Force Base. There's a nearby rail corridor. There's an interstate just to the left. And north, I'm not highlighting here, but there's a U.S. state route, which is a market road, or where agricultural machines or farmers tend to use, given all the farmlands that's surrounding IACT. And also we have the village of Rantoul just adjacent. And so highlighting that apart from the facility, we also have a nice options for validation and also other jurisdictions that we can work with just within a 1 mile of proximity to the IACT. And with the vision, here's a quick snapshot of IACT bird's eye view. What we intend to do is we will have a high-speed loop, and I'll have a video that will kind of take a virtual tour of what we envisioned. But the main, some of the main unique factors that we are excited to pursue is the connectivity of high-speed platooning of freight trucks, which other existing tracks do not have the capabilities to do so. We'll also have a multimodal transport facility here in the left, agricultural land, and adjacent market roads that we can play with, and access to smart and suburban city. Also a facility to invoke seasonal variations. As we know, right now we're all at home, or I hope you're staying at home given the snowstorm that we're undergoing, which is going to be critical issue when connecting autonomous vehicle get on our roadways. So here's a short video, and let me remove the sound. Okay, so we're zooming into the Rantoul. We just saw this map just earlier. And now we're going to be driving through the facility. So we'll start with here. This is the outer loop. Well, we have 3 lanes that the freight trucks can platoon constantly at 75 miles per hour, which will be the fastest speed that a track can host a continuous platoon looping over the entire IAC. We're going now to the inner loop, and that's important. You can imagine that, and maybe related to arterial roads. Here on the left are actually existing facilities. Our lab, ATRL, the main infrastructure of ICT, will have a control tower for new offices. And here, suburban and urban setting for more test cases and scenarios. We'll also have an environmental test chamber where we can subject vehicles to different conditions, and a dynamic testing pad for different vehicles. Multimodal mobility with the rail, and also an agriculture testing area. So trying to capture what are the cases in Illinois and also beyond Illinois that we can anticipate as we're growing into adapting connected and autonomous vehicles. And so what we believe in is also building on Illinois' strengths. As you can see here for IAC, there will be 3 main prongs that this Venn diagram nicely showcases that addresses the vehicle to vehicle, vehicle to infrastructure, V2I, and vehicle to X, or vehicle to everything. So there'll be a slew of different test settings. I've mentioned that the speed can be up to 75 miles per hour. There will be different controlled weather in 4 seasons, urban and suburban. Now with the mode of transportation, we've seen that there will be different modes as we can anticipate what our infrastructure handles. And the infrastructure itself will be connected. And I'm not only talking about, putting sensor in the roads, also in the bridges, potentially a tunnel. And again, these are under talks as we're planning IAC, and also the energy grid as we support electrification and also energy harvesting needs for the track. And this will be coupled with the NCSA as we can anticipate each of these prongs, and it's combined, it will generate so much data. So having the infrastructure not only for CAV or T and the infrastructure itself, but the data itself is quite needed, and we're quite excited to partner with NCSA to do that properly. So I've said some of the key things that IAC intends to focus and harness is high-speed freight platooning, multimodal logistics, also the development of protocols where it really, the findings will boil down to how to safely deploy these technologies and vehicles in a connected infrastructure. We'll also have the variations controlled and actual as we anticipate that, or we experience in all seasonal variations, different types of platforms. We'll also be integrating solar panels, as the plan is to have a net zero energy where the solar panels, wind turbines, and also other energy harvesting capabilities will supply the energy needs of the test facilities. I've highlighted in the map earlier the proximity to Rantoul and then adjacent interstate or local roads. So that also offers validation scenarios for us that can closely relate to the controlled condition we'll have in IAC. And speaking of Rantoul, this is also quite important economically and socially, as Rantoul used to be a really active town, given it was a training ground for the Air Force, but since it's closed down in the 90s, there has been a decline. And so not only does IAC offer opportunities, to incentivize nice research opportunities and collaboration opportunities, but also a direct economic growth within Rantoul and scaling that up to the county and to the state and beyond. And in support of this, from the Investment for Growth program that we were awarded, it will cover, and actually it is covering the planning of the conceptualization that a consultant is currently doing right now, some seed research funding for 3 years, and per year 8 projects, and the first 8 are listed here on the left. And also education and training program are parts of the award for the investment for growth. Today, after my presentation, either Professor Chen or Professor Oyang will be sharing with you what this project is about, modeling and testing autonomous shared multimodal mobility service for low density rural areas. I do want to highlight that 2 other projects will be highlighted next week for V2V sensor streaming and also wireless continuous monitoring. And towards the end of this semester, by April 28th, we will have Professor Kuyat to share their findings related to the quantum communication network. One thing to note is these seed projects are particularly focused on identifying, what are the technologies to include in the IAC planning. And if you want to learn more about their abstract, I put a hyperlink at the bottom. You can visit at the SDII website to get to know more of the project. As I've mentioned, part of this growth program, this grant was also to create a new education training program, which will be a Master of Engineering Smart Mobility. It will be cross-disciplinary. As you can see here, there will be 3 tracks currently under plan right now. First is a certification program for professional students, and then 2 master's programs related to autonomous mobility infrastructure systems and mobility services, economic and policy. Adjacent to that, we also have a IDOT-sponsored project that's focused on identifying what are the frameworks related to 5G electrification and energy harvesting as part of the IAC testing arena, and also the business plan. In parallel to that, we have a project which I'm quite excited to be a part of for Mobility 4.0, which the main idea is to create this roadmap or blueprint to identify within the state of Illinois what are the resources and activities that are happening to clearly prepare and identify Illinois' readiness for connected autonomous vehicles. Now, with respect to the timeline of planning and construction of IAC, a good part of the land has been pledged by Rental. We are working on procuring the additional land, which is really governed by the design speed of 75 miles per hour that's going on the outer loop of the track. We started the feasibility and project approval prior to the pandemic, and last year a consultant was brought in to do the conceptualization and environmental site assessment of the proximity limits of IAC. Hopefully by towards the middle of 2023 is when we'll break ground and construction and instrumentation will happen. And following year after that, we hope to at least have the major roadways constructed to be ready for testing by 2024. I do want to note that these dates are pending to be updated after the conceptualization phase of IAC is completed by this summer. Another interesting thing that that was recently done is an independent economic study by Professor Delerba from the College of Ag, Consumer, and Environmental Sciences. And the idea is starting from the planning phase of IAC, right? So the different supply chain of jobs and expertise all the way to 2050 when IAC will be running and scaling up the level of activities from the plant after IAC constructed. He evaluated that up to over $7 billion in total impact on the state economy can be generated, which corresponds to just a little over $1 billion in total taxes for the local, state, and federal combined, and also up to 53,000 full-time equivalent jobs by 2050. And I cannot highlight enough that we're quite excited to champion how to properly, safely, reliably, and equitably integrate these technologies for the state of Illinois. And as researchers ourselves, or maybe some of my colleagues here at Illinois and other universities, obviously this is quite exciting as we will offer significant opportunities for multi and interdisciplinary research directed for the state. So I hope that, as I provided the background overview of STI and IAC, that you can see that it's quite a nice and clear opportunity for the state of Illinois. And we know that such endeavor is quite ambitious and would need a good amount of stakeholders from government, academia, nonprofit, and also industry to really support this platform investment for smart mobility, and also to ensure that we pursue economic and workforce development. And IACT will nicely utilize, a nice pool of expertise, which we are continuing to grow. You may remember our nearby access to multimodal transport options, also the capability to have a controlled and real life settings of 4 seasonal variations, and with what the main unique factor of implementing freight logistic at high speed of up to 75 miles per hour. We'll also deploy a large scale effort for vehicle to infrastructure and vehicle to everything instrumentation, and have the capabilities to also understand drones and 3D mobility, all of which will be supported through the infrastructure and also additional infrastructure we'll have to boost NCSA's capabilities in 5G and beyond connectivity. And you may remember we'll also have a section for agricultural machines in market for use. And with this, I think that's the end of my presentation. If you have any questions, I'd be happy to answer.
Okay, so if not, maybe we can take a couple of questions at the end too. We have the next speaker, and Angeli, you can go ahead and introduce them.
Yeah. Okay, I think I have stopped sharing. I see Professor Oyang.
Yes, hi. Should I start?
Yes.
Do you see the screen, right?
Yes, we can see.
Okay.
Yes. If you don't mind, Professor, let me just introduce Professor Chen on your behalf.
Yes, please.
Actually, that's what we advertise
for.
Yeah, if you don't mind. Thank you.
Okay. Yes, please. Yeah.
So as I've mentioned earlier in the presentation, Professor Oyang is actually one of the co-PIs for this SDII project. Unfortunately, because of the snowstorm, Professor Chen is unable to join us. But just as a overview about Professor Chen, he's part of the faculty of the Department of Industrial and Enterprise Systems Engineering. His research includes optimization, data analytics, revenue management, and supply chain management. And today, Professor Oyang will be talking about their project on modeling shared multimodal mobility services for low-density rural area. So the floor is yours, Professor Oyang.
Great, thank you, Angeli. And again, as mentioned, I'm sort of substituting for Professor Chen, who is probably now in a plane returning from Atlanta if his plane hasn't been canceled again. Essentially, it was very fortunate for us to be able to work on this STII project, mostly more focusing on the system side of autonomous and then shared mobility services. And then particularly in this work, we were focusing on a little bit beyond the IACT, the test tracks, but looking at the village of Rantoul as a test bed for this, and then how we are going to provide mobility services and shared mobility services, especially for low density rural areas, and which is normally a sort of area that's being sort of less focused upon in the past research. And then so this joint work with obviously our lead in the project is Professor Xin Chen, and then our students Ibrahim Adrian, and then also Haolin Yang. So well, we all know that actually a lot of revolutions are happening right now in the field of transportation, and then a lot of these buzzwords are being repeatedly used, and then which we are very excited to be working on. But I just want to mention a little bit that actually a lot of this work has been done in urban areas, and mostly focusing on congestion. The issue is about the capacity being largely sort of smaller than the demand, and then the congestion arise, and how do we alleviate that? In most of the rural areas, the problem is actually the opposite. And very often it is due to the low demand density. The issue is not mostly the lack of enough demand in order to supply the capacity. Essentially, particularly, it's very hard to justify maintaining a dedicated vehicle fleet, whatever vehicle that is, to serve the demand that are very scattered, very low demand, and very infrequent, that needing service. And then in particular, even using the so-called public transit, it's difficult because it's very often economically, it's just difficult to provide sort of a convenient service with good accessibility, meaning that having a bus stop near every person's home because people are so scattered in a large area. And then this first and last mile issue is really prominent. So what we are trying to look at is that given the autonomy that's coming, and then given these concepts of shared mobility, then how can we actually develop flexible mobility services that are actually going to be suitable for low demand areas, and then particularly focusing on how do we provide the first and last miles to passengers that are scattered. So the major question, we actually this project, we split sort of the two of us each focus on an area, and then we are going to put them together. We are in the process of putting them together. One part is on the strategic level. So in a sense, actually, if you were given an area, for example, you were given a area like Rantoul, like a village, or maybe a certain rural area, whatever it is, then even the first question you should ask yourself as a service provider like Uber, right? You're going to ask yourself, what type of service is actually the best service? And then how many vehicles should I maintain? How many drivers should I recruit, such as I can maintain a certain level of service in terms of the travel time, accessibility, and so on. And actually how feasible it is to compare different types of services such as Uber Pool versus other sort of premium services. Am I going to be able to break even by providing those services, and what are going to be my cost-effective sort of effectiveness? So all these questions from the service provider, but similarly, the government, say the village of Rantoul, would ask something similar, but slightly different. They would say, if I were to allow allow certain service providers to be serving my people, then what can I realistically expect as their service, and how much we should charge them for the or whatever tax, right? Whatever like sort of permit fees that I should provide, I should actually charge the service providers, and then how are my people going to be happy or not happy, whatever. So these are the questions actually we focus on the strategic level in terms of planning the service. Then most of this type of planning services assume that we know the demand, and we're going to be trying to figure out how to put resources together to provide the service and then make people happy. Actually, then Professor Xin Chen and his student has been working on the sort of the mirror side of the issue, is that he has been looking at the operational level and focusing more on the demand side, is that how we can allow the service providers to charge prices and different type of services, and then by doing pricing to control the demand, and actually then try to sort of adjust the service that we can provide. So essentially, we are looking at the sort of the both supply and demand sides of the problem, and trying to make the best equilibrium in between the two. So what I'm going to talk about next is about the strategic part, which is mostly on the supply side. So again, the question is here: how do we provide services? What type of services to provide? So one of the easy way to solve the problem is using the so-called flexible route transit concept. This is actually has been in operation for decades, sometimes under the term of a paratransit. But really, the idea is actually, instead of having fixed transit, especially when demand is low in a rural area, instead of forcing everybody to go to bus stops and then wait for the bus to come, and the bus always travel on a street, sort of a certain route, we allow the buses to come to your door and pick you up. And then this type of services has pros and cons, obviously. Then the vehicle has to travel longer, but the people can save the trip from going to the bus stop. And it's beneficial for low demand, because when demand is low, the fixed route, traditional fixed route buses would have to have very long sort of a spacings between the stops and between the lines, and people have to walk a long distance. Just because there are very few people, they have to walk long because they're not important in a way, because their sort of a passenger cost is insignificant compared to the cost of providing the service. So it will be undesirable. So the idea of a flexible transit has been in discussion for decades. And then some of the work we did under in this direction is about maybe we should actually do a sort of compromise in between, such that actually instead of actually having the vehicle come all the way to pick up everybody, maybe it's also beneficial to partition the space into some sort of catchment areas, and then allow people still to travel a short distance, and then the bus to come around and then visit those certain stops, and then pick up people from certain gathering points. And then there's some results from our previous work about how to optimally partition space into catchment areas for each bus stop, and how we route vehicles around those stops. There's some optimum shape, which is hexagonal, and so on and so forth. So using those results, we were able to develop bus services such as, we can allow buses to be sort of having some flexibilities, but even allowing skipping stops when the demand is really low. Only when passenger shows up at a certain location, they call for need service, then we will visit its neighborhood and pick up the passenger. And then we have this whole sort of framework of designing such systems. And in some earlier efforts, we did some testing with some real world data from Qingdao, China. Then we were able to show that our performance such system is already very good. We can actually improve double-digit percentages in many attributes, such as passenger, sort of their travel time and their fulfillment rate, and then the occupancy of the vehicle. And so all these different things, we were happy that this is actually seems to be a promising way of actually providing services to rural areas. Then RAN 2 probably will be our test bed also for this, and then we can implement very quickly on this. But then we also looked into some other directions for providing services. Really, the service, we understand mobility services for rural areas has so many different options. Every company could come up with something intelligent and innovative. So traditionally, we allow people to drive, we allow people to take the fixed route transit, but really there is a spectrum of alternatives. And then people have been, in the recent 5 years, people are very creative. So we have taxis that are almost like driving, but allow people to share vehicle over time. We have shared taxi to allow a few people share vehicle even at the same time, right? Their ODs has to be, their origin destinations has to be aligned in time and in space somehow. And then we allow direct ride or customized buses, even allow more people to share vehicle at the same time, but they're really flexible. And then the route is totally dictated by the origin destinations of the passengers. And then we have some transit plus shared vehicles. All these are just some samples of opportunities that we can explore for rural areas. But then here, one of the efforts we made under this STII project is to try to explore some sort of a combination across all these shared on-demand mobility services here, the taxi, shared taxi, and the direct ride. We actually showed that actually there's a unifying framework that we can use to analyze all these services in one mathematical framework. So what we did is that they all share the feature of a random customers showing up over some space, over some time, and then we have limited number of vehicles, and then we allowed some of them to share vehicle at a time, and then we use these vehicles to move around to pick up and drop off passengers over this confined space. So they sort of share some physical similarities, although they operate very differently. So what do we try to do is actually we build an overarching model to try to understand all these services, and all these services will be special cases of our mathematical model. So just to show you a few things we worked on. But the first thing is that actually, no matter what is going on in an area, we are having taxi, we are having Uber pool, whatever, then we understand a whole bunch of vehicles are moving around to serve the passengers. And then the vehicles could be in many different states. So just to really quickly show you that, this I hope it's straightforward. So this basically, the chart on the right shows you how a vehicle, which is a rectangle, can be picking up a passenger on its way to, for example, this is picking up on the way, this is an empty vehicle. The vehicle could be empty at some time. The vehicle could be going somewhere to pick up a passenger. The vehicle could be having a passenger on board. The vehicle could be picking up 2 passengers on its way. The vehicle could be having 1 passenger on board, 1 passenger still to be picked up, and so on and so forth. So we can keep doing all these things and then understand all the arrows showing the transition. This transition each happens when a pickup or drop off happens, right? So the vehicle, every vehicle in our service system can be uniformly sort of described as in one of these possible states, like conditions. And then we understand that each of these states has a duration. It's when the vehicle is en route to pick up somebody, or it's en route to drop off somebody, and so on and so forth. And then just understand if the vehicle is actually, I should have a little, this simple simulation shows how the vehicle is moving around in a continuous space, but then keep changing you can see the marker is changing after picking up or dropping off some passengers. You can imagine a city in a rural area, a certain area, the vehicles, a group of vehicles that just keep moving like that and changing state along with that. But no matter what, the vehicles are going to be in one of those states that we can predefine, and then we can sort of model the time it needs to be in each of the states, and we can understand its evolution over time. Then we will be able to understand, how a lot of things about these vehicles in terms of the service. I'll just skip this. Just say we come up with a overarching model, and we predefine all the possible states of the vehicles in terms of the passengers it has on board and the passengers it's still yet to be picked up. Then we understand the vehicle. Each of these circles is like a possible type of vehicle, like a state of a vehicle. Then any vehicle in your system is going to be moving around these circles around based on the sort of dynamically, randomly. And then remember the simulation, keep changing markers. It's moving around these circles. Each of them is like a container with vehicles in it. Then we understand the change of state is based on you give the vehicle a new customer, or the vehicle actually just picked up customer, or the vehicle just dropped off a customer, then the vehicle just keep flowing according to the arrows randomly in this network. With this, we're able to show that actually almost all of the whole range of services in a city or in a rural area can be special cases of this big triangle. Then essentially, you can define whatever triangle you want to look at, and then you can build a model like this. This will keep track of the evolution. This example here, shared taxi, is exactly the one on the previous slide. We just rearranged the 6 states into a semi-triangle, into a triangle, and then I hope you can see how the transition of state could happen. So with this, we can keep track of the vehicle, sort of all the states. We can also keep track of how long it would take for the vehicle to shift from one condition to another. This requires us to do some mathematical modeling. For example, particularly in the shared mobility context, we need to understand if customers randomly show up and the vehicle randomly move around, what is the expected distance or time it would take for a vehicle to serve a passenger to do whatever. We need to know how long it would take for the vehicle to finish a job, whatever that job is, either pick up or drop off. So there are some mathematical results that we have from the literature regarding if you have N passengers, you pick up one person that's nearest, how long it would take. If you take all of them, then how long it would take. But then we actually further did some new work. If we were to pick up out of capital N people, we need to pick up a lowercase n of them. So we only need to pick up a subset of them, then our vehicle capacity is going to be reached, for example. Then how long it would take for us to do that, right? So this could be applicable to several of the situations we may have in the shared ride context. We have analytical formulas for that. We were able to show that it's actually quite accurate. We were shocked how accurate it is. Then essentially we have formulas to understand how long it would take for vehicle to finish jobs. Then we are able to actually do a lot of things to model how long, essentially a Markov chain. We understand how long the vehicle is going to be in each state and so on and so forth. So we will have a very good description about the city or the rural area already. And then the last part that I just want to quickly mention is that because we're doing ride sharing, we would want to match customers together. Then certain type of customers, for example, one origin, one destination by one passenger and another passenger. How shall we use the same vehicle to serve them, or should we use 2 vehicles to serve them? That's a big question. So this has to do with temporal and the spatial alignment of their trips, right? There's origin destination better be in the same direction. Their travel time should be close to each other. Then they can comfortably share the same vehicle. Otherwise, it will be mad if we force them to share the vehicle. So with all these considerations, we were able to develop models to understand the probability, how much of alignment is a good alignment, and so on. And then the cost associated with forcing people to be sharing the same vehicle in terms of the vehicle has to be detoured, and also the delay, people have to wait for each other in a sense. Then we were able to derive all kinds of impacts of such sharing operations. And then we come up with very good formulas for that. And then basically we were also able to show that with the simulation, I showed you this already, then we are able to measure our formulas, the model that we came up with actually matches with the simulation almost very well. Let me just say it's very well matched with us. So we're very happy. That means that our formulas are probably reasonably correct. So with this, we are able to utilize this framework to analyze a sequence of services. We can actually analyze the traditional transit. We can analyze the flexible transit, so the flexible route transit. We can analyze direct ride, customized buses. We can analyze shared vehicles, shared taxis such as Uber Pool. We can analyze the traditional taxis and then automobile driving, individual. This chart shows just we can analyze all these systems using the same framework, and we're able to show you how the customer service received, the door-to-door travel time for a passenger, expected travel time, is related to the fleet size you provide. And this different curve, this red dashed line is sort of the efficiency frontier, tells you under different investment level, given a certain demand, or this whole chart is a given demand. This demand density per unit hour, kilometer square, how many people will show up for service. Given that, we can do this for every service we provide. And then this gives you information about, if you give me Rantoul, which is this plot is already given the demand, then what is the best form of service we should provide that will actually provide the best service with the least cost? If you think about the fleet size is the investment level that the agency or the operator has to put in, then the y-axis is the service we can provide. Then we can actually choose whether we should use conventional transit if we really don't have any vehicles we can afford, or we can use different services or taxis, just simple taxi if we can afford a lot of vehicles. So this helps the decision makers decide what service to provide and how big it should be, the service should be. Okay, so with this, I think I covered a little bit about the strategic level, but one strong assumption I mentioned about is the fact that actually all the things we are doing here is assuming that we know the demand. We have been assuming that there's a certain customer demand rate that shows up, per unit time, per unit area. But then that's actually, in reality, that's not the case. Whatever planning we do, we make assumptions about demand, but in reality, things are different. So what Professor Chen and his student has been working on mostly is about how we can further improve the service if we were to utilize the operational level decisions, such as pricing and the service option sort of offerings, so as to sort of affect the demand. We can actually, for example, here, we want to, so basically the idea here is that in the real world, day-to-day operations on the order of minutes, whenever a customer shows up, we can give the customer different options. We can give them different vehicles, we can give them different prices, and then we can give them sort of different promises on the time that they're going to be picked up and dropped off. So with all these different options and different prices, we will be able to influence demand, no longer assuming the demand is fixed, but rather we allow the demand to be influenced by us. And then we can achieve whatever extra goals that we want to achieve, such as we can maximize revenue if we were operators or Uber, for example, or we can try to somehow maximize the social welfare if this is we are representing the village of Rantoul. So all these things we are doing on the next level of decision making here. And we also understand that actually some people may be more sensitive to the delay. So for example, here, the right-hand side here, the chart shows whenever a passenger calls for service, then we could give them different vehicle times. We can give them different pickup and drop off times. We can charge them different price. People may have different choices. And then in that way, we are able to, by giving those different choices, we're able to affect the demand a little bit for our supply input. So this is what Professor Chen has been working on. And then particularly the two sort of challenges. One is that actually this type of decision needs to be done in real time. It has to be, all these uncertainties in the real world has not been considered in the planning model. We make some expectation type of decision making, but then the reality, there could be delays, there could be snowstorms like today, then traffic may be congested and whatsoever. So there are a lot of challenges that are here. So I think the real-time decisions involves how all the vehicles should be routed. This is going to be really sort of a detailed, like the exact routing stop by stop where to go, and then the pricing to manage the endogenous demand, like how to charge prices, and then also assortment means actually which among all the vehicles I have running in the city or in the rural area, which subset of them I offer to the customer, so they choose among the subset, right? And that's how it has an impact, obviously, to the operations, and also the time that we promise regarding the pickup and drop off. So people are going to look at all these different things, and then as customer, they're going to choose one of the offers. And also the challenge here is that actually things are dynamic, in the sense that actually whatever you decide regarding one customer, you use a vehicle to serve them, you offer prices, whatever, that's going to affect your future customers. The next customer shows up, you have already used this vehicle, this option. So you have to sort of sometimes even it's wise to reserve capacity, reserve vehicle for a next customer. If you know another customer is going to show up, it might be good to sort of take that into consideration, right? You reserve some vehicle, you know that some big, important VIP is going to show up, and you will really, get ready for that. So those type of decision is really sort of interdependent over time as well. So I just want to, I think this is an example that Professor Chen prepared. I just want to briefly mention it's fairly straightforward. So essentially at a certain time, you have two vehicles serving, sorry, I'm running a little fast, but here, this vehicle currently here, picking up somebody, dropping off somebody, another vehicle, picking up somebody, dropping off somebody. But another passenger OD3 shows up. It could be this 3 OD, origin destination, can be served by vehicle 2, can be served by vehicle 3, served by vehicle 1, I'm sorry, and served by vehicle 2, then these are different options. And then the platform needs to decide which vehicle to use and how to insert this new customer into the existing vehicle's trips, and then decide to serve them. And then how this is going to influence the future. There's all these are, this is sort of the decision they have to make in the sort of here. So really here, the problem, I think I already explained that, the whole decision is sort of in a dynamic decision-making process. We keep, whenever a customer shows up, we decide what to offer to the customer, what price, what options, and then we decide how do we best utilize the vehicles we have in anticipation of the future. And then this, so my understanding, the model is actually built as a Markovian decision process. Actually, it's quite similar to what we discussed earlier in the planning model. We are going to describe the vehicle, each vehicle state in terms of where they are and who they are serving, where they're going, and then we are going to try to understand the users as well, their behavior based on the certain options and the utility functions and so on. So that's sort of here the details. So I will just briefly mention that this dynamic decision-making process here is new in a sense, in a lot of sort of a complex real-time decision-making that's going here. Okay, and then just a little bit about I think I will probably go rather quick here in terms of the decision-making options. So routing is one part of it, essentially how the vehicles are going to be routed through new and old customers that they already have. And then another decision dimension is actually when the platform is deciding the promised pickup and drop off times for the passengers, then essentially sometimes it's wise to try to leave a little bit buffer. So that actually you don't default on your promises to your customer. So, but how much is too much? If you promise too much, the customer may just actually just ditch you, right? But then otherwise, if you promise reasonable, and then you may be able to get the customer and yet give yourself a little bit flexibility for other customers. So essentially this buffer is a big decision here in operation. How much do you promise? And then some other decision, again, already mentioned the price for each subset of vehicle. Which vehicles do you offer to pick up the passenger? And then what prices are associated with each of them, and so on and so forth. But I understand that actually, if we were to put all these things into decision, really when we are deciding which vehicle to go pick up the next passenger and at what time, these are all our decisions and how much we charge for that. We need to really, in order to make that decision, we really need to understand the entire operation of the system or the entire state of the system. We need to know exactly at the moment of decision making, where are my vehicles? And how are the vehicles look like? Do they already have a passenger on board? Do they have somebody they still yet to be picked up? And then do they have, essentially, I need to know everything about how the entire fleet is looking at, and all the other customers are not to be picked up. I need to know all this different information. This information that actually gets into serve as a basis for me to make a decision. So in the so-called Markovian sort of decision-making process, we try to approximately optimize the problem through the dynamic programming algorithm. And then essentially the idea is actually if we have a complete description of the vehicle state and the customer state and so on, then we come up with a so-called policy. The policy essentially is that whatever you take a photo of the system, and then that photo is going to trigger a mapping from the photo to a decision about which vehicle you should use and how, routes, price, and so on. Then I'm gonna then trigger me an action to follow next. And then in order to do the ADP, I'm not gonna go into the details, but essentially the whole idea is about we need to have a value function, so-called value function. It's sort of the relative value of a certain state of the system. Like if you have a vehicle that are having a certain spatial distribution, certain occupancy of passenger allocation, and so on, then that is a state. In that state, you just imagine how much is that worth. It's like an asset you are trying to sell, right? You can say, how much is that worth relatively if you have a different vehicle distribution, that different location, a different vehicle occupancy state, how much value is that? This is essentially evaluating that, if you were to, when you are assigning new passengers to new vehicles, you are essentially changing the system state from one to another. You are changing the vehicle from their current state to a new state, and how much is that change affecting the value of the system that you are trying to optimize. So essentially, this whole approximate dynamic program is trying to find a way to assign the value function quickly. So I'll go really quick. Just to say that actually this problem, as you can imagine, to describe the entire fleet, it's challenging because there are a lot of states. We need to the state of the system. Even one vehicle, it includes the remaining capacity of the vehicle, list of passengers that are already to be served by this vehicle, and then the passengers who are not yet picked up by the vehicle. So we have to keep track of everything, literally everything that's ongoing. And then you can imagine if we have many vehicles, and this is gonna just be huge. The state to describe the system, it takes a lot of information. So I think Professor Chen and Ephraim actually developed some ways to aggregate the state. Essentially, there are so many states, it's becoming intractable. They try to find a way to aggregate the state, identify which dimensions of the states are important and which are not. And then they were able to reduce the dimension of the states and then make it manageable. This slide is about that, and they did all this nice work. They were able to use approximate dynamic programming to solve the problem. Then they also test their approximate dynamic programming method, the policy they get from their model, to some simple models and simple policies that otherwise people can just think of. Then they were able to show, I think I would just say that they were able to show with some test cases already there are significant benefits that are obtained by applying the model they have. So the contribution is that really this dynamic operational level decision making, they were able to come up with optimization framework to address the demand management side of things in a real time. Very complex problem being solved, by observing the structure of the problem, and then I think I'll just skip it. The problem can be solved within milliseconds, so it's actually very nice. Just the last part, I promise within half a minute, 1 minute is actually the last part we are still working on. Our project is ending soon, but then as a seed project, but we see this as a starting point for some new project in the future. We are putting everything now into an agent-based simulation platform, and particularly for RAN tool. So my student actually got this OpenStreetMap. We're using some software. We were able to convert any street map, the map really, into a network representation. This is a RAN tool, and then the village of RAN tool, and then this is automated. This whole thing is actually automated, and then we were able to do some treatments about how we are going to do the vehicle roads and so on, and also the agency, the operator decision making, and the passenger decision making. We put them all into the agent-based rules, and then we are able to. I hope this will show. This is just a preliminary show of the vehicles in RAN tool. Customers show up at random points, and then we have vehicles I think the dark ones are actually loaded by passengers, and then the blue ones are idle vehicles. Customers show up, vehicle go around and pick up. Then this is sort of a still work ongoing, but then essentially the idea is that we are gonna able to simulate the system performance for a real world network, and then we were able to see how the predicted performances that from our model is going to be able to apply to a realistic RAN tool testbed here. So with this, I think I'm out of my time, and then thank you for your attention. Thank you. Oh.
Thank you, Professor Ouyang. I think due to time constraint, we do have a space for one question. You may either raise your hand or the chat, or unmute yourself. Okay, go ahead, Egaben.
Hi, well, thanks a lot for both presentations. I actually have a full question about the full track, if that's okay. Have we thought about incorporating bridges and different type of bridges at different deterioration states to see how transportation affects those types of infrastructure too?
Yeah, the short answer is yes, but depending on the option that we're going with the conceptualization, we may vary the number of bridges from 1 to 3, but absolutely in your concern of structural health monitoring is part of the wish list, if you may. We just have not identified the details. We also have talked about the possibility of also a tunnel, right? Because the rehabilitation monitoring and then the associated connectivity also changes when you have a tunnel versus a bridge. So it's still kind of up in the air that we're discussing in details as we speak.
Thank you.
Professor Ouyang, I do have a question for you. on that last nice simulation that you showed, can the model easily take constraints? Say if there's like a roadblock or construction, how is that taken into account? And also, with the rural and the idea of improving, the economy there, how would, this framework change if we were to connect this, say, to Champaign?
Well, sure. Thank you. The first question regarding the roadblock, that's fairly easy to incorporate. This for the simulation. The modeling will be much more difficult, but the simulation wise, we just need to. It's essentially just removing some lanes for some time, right? Like removing some links in the network for some time. Then this algorithm force the vehicles to be traveling on the network based on the shortest path and so on. And then if the link is removed, it's automatically looking for the shortest path in real time. So it shouldn't be almost like what Uber does anyway. They give the driver the directions, right, in real time about the congestion. Even congestion can be incorporated fairly easily as long as we know what's happening. So essentially, the first part of the question is fairly. I think we can do that, no problem. The second question regarding connecting to Champaign, if I understand correctly, you're saying that if we consider Rantoul and the Champaign as a whole for simulation?
Yeah, because the demand will change. There's a spatial difference, and I guess I'm just imagining if someone wants to travel from Rantoul to Champaign. So you have two different data sets with two different demands, and the routing and all that stuff. How will that change if you provide that route inherently to a rural area?
Actually, in theory, the whether we include the Champaign in this network is not a concern. It's essentially actually from a modeling point of view, rural versus urban are very vague sort of subjective definition. We could have different areas in one network that have different demand density. So when we talk about rural urban here, we were mostly referring to the fact rural area have much lower density of service. The demand is much lower. So, but then this model type of things we're building, at least for simulation here that we're showing, there's no such sort of a rigid definition say it has to be a certain range of values of parameters. You can be just having we can easily put the Champaign also on the map like a connected network. And then the OD demand, essentially it's just actually think about OD demand. We have different zones with even within Rantoul, we have chopped up this city or village into small pieces, and we know the number of people per unit time going from this area to that area, right? So then we can easily expand that into a bigger matrix, and then just however the demand is going to be, we can just accordingly do the same thing. So I think it shouldn't be any problem as long as it's something of that's needed. It will be easy to do potentially.
Gotcha.
Yeah.
Awesome. Well, thank you so much, Professor Ouyang, on behalf of Professor Chen. And thank you to everyone who attended this week's Kent seminar. Please watch out for the other two SCI project highlights that we'll have next week, February 10th. It'll be about V2V sensor streaming and also wireless continuous monitoring for IACT. With that, thank you, Professor Ouyang, and thank you everyone for attending this week's Kent seminar. We'll see you next week.